Welcome to this explainer. Today, we're going to uncover the physical foundation of literally all modern electronics, the printed circuit board, or PCB. Think about it. If you've ever held a smartphone, typed on a laptop, or honestly even just run a cycle on a modern washing machine, you've interacted with the invisible engine that powers our world. So we're going to explore exactly what a PCB is, why on earth it was developed in the first place, how this incredible tech evolved over the decades, and why it's absolutely crucial to every single piece of tech we rely on today. Let's get into it.
Okay, let's kick things off with a pretty intriguing question. How exactly do lines of digital code make a physical robot move? It's kind of wild when you really think about it. I mean, software's just code, right? It's totally intangible, just logic, instructions, and data. But when that code tells a massive robotic arm to lift a heavy box, a physical action actually happens in the real world. So how does that work? Well, software provides the intelligence, sure, but you absolutely need hardware to sense, process, communicate, and act. The PCB is that vital physical bridge connecting digital instructions to real-world actions.
Section 1. The city inside your tech. Understanding the PCB infrastructure.
To really wrap our heads around this, imagine an electronic circuit as a bustling, thriving metropolis. The electronic components, the resistors, microcontrollers, and sensors, those are your buildings. The copper connections running between them, those are the roads. The electrical signals zipping back and forth are the vehicles. And of course, the power lines supply energy to keep the whole city running. In this scenario, the PCB is the ultimate, master-planned grid keeping everything perfectly organized. Without this meticulous planning, managing all those connections would be a total disaster. The PCB ensures every single component sits in its exact, designated spot and connects precisely where it needs to.
Now, you might hear the terms PCB and PCBA thrown around, and it's super easy to confuse them. But the difference is actually really simple. We have to distinguish between the bare land waiting for development and the fully populated city. A PCB is just the bare board. It has the conductive patterns, the drilled holes, and the protective coatings, but honestly, it can't do anything yet. It's an empty grid. It only becomes a PCBA, a printed circuit board assembly, after all the active electronic components are mounted and soldered right onto it. So a bare board designed for a robot can't actually control anything until it gets fully populated and becomes a PCB.
Moving right along to Section 2, before the printed circuit. And let me tell you, it was a complete wiring nightmare.
Picture this. Before PCBs came along, looking inside a radio was essentially like looking at a metallic bowl of spaghetti. Circuits were built using point-to-point wiring. Workers had to attach components to a chassis and physically solder individual wires between them by hand. Imagine doing that for early communications equipment. People were following these ridiculously complex diagrams, cutting and soldering every single connection manually. It was excessive. It took up massive amounts of physical space, and worst of all, it was highly error-prone and inconsistent. Two people could build the exact same circuit differently. Just one wire on the wrong terminal, and boom, complete failure. PCBs completely replaced that chaos with planned conductive paths that are compact, reproducible, and incredibly reliable.
Section 3. An evolution of innovation. From early patents to modern microboards.
So how did we get from those bulky spaghetti wire radios to the microscopic smartphones we have today? Well, it didn't happen overnight. It started way back in 1925 when Charles Dukas patented some early printed conductor concepts. But things really got moving in the 1930s with Paul Eisler, who's known as the father of the modern PCB, when he developed methods using metal foil. Then, the 1940s hit. The massive demand of the Second World War drastically accelerated the need for compact, rugged electronics. By 1949, Abramson and Danko invented the auto-assembly process, allowing automated soldering. The industry just exploded from there, standardized in the 50s, until a massive leap forward happened in the 1980s.
That 1980s leap? That was surface mount technology, or SMT, and it was a total game changer. Before this, components had these long metal legs that had to be inserted entirely through holes drilled into the board. But SMT flipped the script. Manufacturers started attaching components directly to the conductive areas right on the board's surface, no drilling required. This unlocked the densely populated microboards we use today. You could place parts on both sides of the board, making products significantly smaller and lighter, while enabling lightning-fast, high-volume automated assembly. Honestly, this specific leap is exactly what makes your smartwatch possible.
Section 4. Why PCB technology matters. Scaling from prototypes to millions.
Why is this physical layout the absolute bedrock of modern commercial success? Simple. Manufacturing magic. Without PCBs, producing complex, affordable electronics on a global scale would literally be impossible. Think about scalability for a second. Once a PCB design is approved, you use that exact same design for a single prototype or 10 million mass-produced units. Every single one is perfectly consistent. Because we're entirely replacing manual wiring with compact interconnections, machines can take over the automated assembly and soldering. This plummets the cost per unit and speeds up development. Plus, you get power, processing, sensing, and communication perfectly integrated into one tiny, incredibly efficient space.
Section 5. Bridging Software and Reality. This is where code finally meets the physical world.
Let's bring this all back home and look at our daily lives. From the Wi-Fi router on your desk to the washing machine in your laundry room, PCBs are the invisible hardware running the show. Let's go back to that robot example. The software tells the robot what to do, sure, but physical sensors have to gather data, a processor has to interpret it, and control circuits have to physically spin the motors. The PCB is the grid connecting all that together so the software's commands actually result in lifting a box. Or your washing machine. That's a PCB managing the wash timing, the sensors, and the motor. Your Wi-Fi router is using a PCB to handle crazy fast data processing and network communication. It's the whole shebang.
To wrap up this explainer, I want to leave you with this defining thought. If software provides the intelligence, the PCB provides the body that actually gets the work done. It's not just a slab of plastic and copper. It is the organized physical and electrical foundation that turns a brilliant concept into a tangible, repeatable, manufacturable reality. It took us from a sprawling, hand-soldered mess to the sleek, reliable tech of the modern era. So next time you grab your phone or start your car, take a second to appreciate that master-planned electronic city hidden inside. But as we rush headfirst into the eras of artificial intelligence, quantum computing, and biointegration, you really have to wonder, what will the physical cities inside our tech look like tomorrow? Will the invisible engine remain aboard, or is hardware about to evolve into something else entirely?